this solution in order to automate the whole procedure of spatial data integration. So after analyzing the origin of this conflicts, we broke down the problem to sub-problems to come up with an automated solution. So here you can see an overview of our solution, which consists of two phases. So we can look at our solution as a validator step that with each merge, it first tries to identify the probable conflicts that exist in a merge using the spatial and non-spatial features of objects. And then in the next step, it tries to resolve them with some minimal interaction with the dominant sphere. So first, we assume that the merging datasets and the system database are both in a consistent state, which means that there is no conflicts between any two objects in the merging datasets, and there is no conflicts between any two objects in the system database. Which means that for each object in the merging datasets, there can be 0 or at most 1 conflicting objects in the system database. Therefore, now the goal is to find the most probable conflicting objects in the system for each object in the merging datasets. Therefore, in conflicts identification phase, we define a conflicts probability function that which indicates the conflict's likelihood for a pair of objects based on their similarity. Finally, we put a threshold on the probability value to separate the conflicting objects from non-conflicting objects. So to define the conflicts probability function, we propose an IR-based solution. In a typical information retrieval or IR problem, usually a corpus of documents are ranked based on their similarity to a query. So in this context, in order to find the most similar objects in the system to a query objects in the merging datasets, we needed to rank the geospatial objects in the system based on their similarity to the query data to the query objects in the merging datasets. So as mentioned, a geospatial object consists of a set of spatial features and a set of non-spatial features, which are mostly textual, such as the name of the entity. So therefore, in our IR-based solution, we define a similarity measure that takes both spatial and non-spatial features of objects into account in 2 steps. First, to make sure that we're not checking all pairs of objects for conflicts, which can take lots of time in some cases, we define a search space filter, which means that for each query object in the merging datasets, we only check those objects, check its adjacent objects in the system that fall into or overlap with the searching area around that query object. And then in the next step, to calculate the non-spatial similarity of the pair of objects, we adopt a state-of-the-art IR algorithm called BM25, which is a variation of TF-IDF to score the adjacent objects based on their non-spatial or textual feature similarity. To implement our solution, we used Apache Solr, which enable indexing and fast retrieval of geospatial data. So here to explain more about TF-IDF. TF-IDF stands for term frequency inverse document frequency, and it's a weight that is calculated for each term in a document based on the frequency of that term and the importance of that term, which is indicated by its inverse document frequency, or IDF. So in our context, documents are textual features of objects. So first, a vocabulary is built using all the unique words in all documents. And then a vector is generated for each document using the TF-IDF weights of the vocabulary terms that appear in that document. After transforming all documents to basically all the objects to their corresponding TF-IDF vectors, we calculate the non-spatial similarity of the query object to each system object using the cosine similarity of their corresponding TF-IDF vectors. Then we boost this value using the inverse distance of each adjacent object to achieve the final score for each system object. We defined 3 research questions. So in the first 2 research questions, we wanted to see how accurate our method performs in different scenarios with different levels of object densities and different points of interest or POI types. To answer these questions, we designed 4 experiments. In each experiment, 2 data sets are being merged, while we take one of the data sets as the system database and the other one as the merging data sets. In the first 3 experiments, we changed the object density from low to high to see the effects of object density. And in the 4th experiment, we changed the POI type from restaurants to real estate agencies to see the effects of POI